Okay, we're going to look at sections 3 and 4. 3 deals with equilibrium expressions involving pressures. Okay, we can use the relationship between pressure concentrations for gases to kind of rework our PV equals nRT, to kind of put concentration in there and then actually use these with equilibrium. And instead of doing brackets for molarities, normally what we deal with for concentration, we can do uppercase P for pressure. Okay, so notice how they look the exact same there. One has the brackets and the other has P. Okay, you don't have to have the parentheses. Sometimes you see it with parentheses, sometimes you don't. It doesn't really matter. The big thing is you see that it is KP and we need the uppercase P. You cannot do KP and then say that it has to have a bracket. You cannot do that. Okay, it has to have P for the pressure. If it's a gas, you're usually dealing with pressures. Not always, but usually. Okay, so now we're going to do the practice problem for the formation of nitrosyl chloride. I have a pressure for the NOCl, a pressure for the NO, and a pressure for the Cl2. And then I have my reaction, and I'm going to calculate the Kp for this reaction. So it's done the same way as a Kc, just with pressures instead. Okay, so first thing I want to do is write my expression. I'm going to have Kp equals, and we do the pressure, and we're going to do products over reactants, so the pressure of NOCl over the pressure of the NO, and the pressure of the Cl2. Now the NO has a 2 in front of it, so that has to be squared. Okay, so all I'm going to do is plug my numbers in. So I'm going to have the NOCl over the NO and the Cl. So NOCl's pressure was 1.2. Oh, sorry, I forgot the other part. That has to be squared. It has a 2 in front of it as well. So then I have my 1.2, which is going to be squared, over my NO, which is going to be basically 0.05. And that's got to be squared. My Cl2, which is basically 0.3. And then all I got to do there is then solve. And I should get 1,900. Okay, and that is my Kp. That is a really, really large equilibrium constant, which means I have lots and lots of products, which basically means what we call it lies to the right. We have lots and lots of products. Lies to the right side or my product side. All right, so let's look at the next thing here. Okay. Now we're convert between Kp and Kc. Sometimes you see K as Kc and sometimes you see it as K. It's the same thing because the Kc sometimes is used for concentration or sometimes people will just put K. It just kind of depends. All right. The big thing here is that on the new thing here, you can't really tell right there, but you can tell better on your paper that delta N. Okay, that's the sum of the coefficients of the products minus the sum of coefficients of the reactants. And again, it's got to be gases you're dealing with here. For a Kp, you can't have the pressure of a solid. But it's the exact same way. And this equation is on your equation sheet. So let's go ahead and try and convert between the two here. All right, so we're going to use the Kp value of 1.9 times 10 to the third, which we just found in the last problem. I'm going to calculate the value of K. Okay, so Kp equals the K times RT to the delta N. So I got to know my delta N. Okay, delta N is going to be my products minus my reactants coefficient. So my product is 2 minus 2 plus 1. Okay, which is basically 2 minus 3, which is going to be negative 1. So I have my K P value, which is 1900. That's going to be equal to my K that I don't know, times RT. R is that 0.08206. It's that number, not the 8.31, because we're not dealing with joules here. It's a normal gas constant. Okay, and this is times 298, and that is to the negative first. Well, negative first basically means on the bottom. So basically, we just got 1900 equals K all over 0.08206 times 298. Just got to cross multiply there, and then solve for K. We should get 4.6 times 10 to the fourth is your value of K there. So it's really easy to convert between Kp and Kc or just K. Okay. All right, the last thing here is heterogeneous equilibria. Okay, heterogeneous equilibria means that you have different, okay, hetero, you have something that's different. So here we're dealing with different states of matter. Okay, before we had only discussed things that were all in the same phase. And those are homogeneous equilibria. They're usually going to be things that are like all gases. Okay, you're not going to have all liquids or all solids, you'll see here in a second. Okay, but they're going to be things that are basically all gases. Okay, and it's more normal to have equilibrium that includes a solid or a liquid. All right, and that's going to be heterogeneous. So heterogeneous equilibria deals with more than one phase. And they're written a little bit differently when you're dealing with equilibrium expressions and concentrations here, okay? So for example, we have this reaction, and it's kind of hard to see on mine, but this guy here is a solid. Oops, sorry. This guy here is a solid, that's a solid, and then this is a gas. So if I were to write my equilibrium expression, okay, you'd be dealing with that, okay, products over reactants. Now what actually happens, okay, and what you put here underneath is that the position of the equilibrium doesn't depend on the amounts of a solid or liquid. So equilibrium, put this underneath, you've got a spot there. Not solutions, okay, or gases, but solids or liquids. Liquid and solution, not the same thing. Okay, it doesn't matter because your concentrations can't change. So they are not included in the expression. All right, we don't put them in there because their concentrations of a solid or a liquid aren't going to change. Okay, because concentration is dealing with moles per liter. Well, solids aren't going to change there with the liters, and neither are your liquids. All right, but pure liquids, not solutions. So we look back up here at this K, CaO we can't put in there, and CaCO3 we can't put in there because they're both solids. So really, my K is actually just the concentration of CO2, and that's it. That's all you put in there. All right, so we're going to look at these two examples. Okay, write the expressions for K and Kp for the following processes. The first we have is solid phosphorus pentachloride. So I got to write the reaction out for these. So phosphorus pentachloride, so Cl5, decomposes into phosphorus trichloride and chlorine gas. All right, we got to watch your states of matter here. Solid for this one, it tells me liquid trichloride and then chlorine gas. So both of those first two are not in my reaction. Okay, for the K, so my K is really going to be products over reactants, and the only thing I have is Cl2. You can put a 1 on the bottom if you want to, there's just nothing there. The same thing would go for the K, P, and be the pressure of my Cl2. All right, so let's look at the last one. It says deep blue solid copper 2 sulfate, so copper sulfate, sulfate's 2 negative, copper 2, it balances out. It's heated to drive off the water. Oh, it's pentahydrate, sorry, so we got our pentahydrate. It's heated to drive off the water to form solid copper sulfate and water. And if you're heating it, the water is going to be in the form of a gas here. This is a solid, and the first one they tell me is a solid. So again, the only thing I'm dealing with here is my K of the water, because the both other two are solids. And we do the fifth. Kp would be P of H2O to the fifth. All right. Now, if your water was on the other side, okay, so if this water, if our products and reactants would have been flip-flopped, okay, you would have written that as 1 over the H2O to the fifth, okay. So if you come across one of those where everything on the product side cancels out or we don't use it, it just becomes a 1, all right? And that is it.